Design of C-shaped patch antenna for multiband. Applications. Abstract. In this article, a completely unique design of multiband microstrip patch antenna has been presented for multiband applications. The C-shape antenna is meant on FR4 substrate and is fed through 50 ohm microstrip feed line. 3 L-shaped slots are introduced in antenna for size reduction and to supply multiband characteristics to realize bandwidth enhancement. The simulated results show that the antenna operates in 2 different frequency bands having resonance frequencies at 4.4 GHz, 6.6 GHz. The antenna exhibits good return loss of 21.0 dB at 4.4 GHz, 12.9467 dB at 6.2 GHz. The proposed antenna has stable radiation patterns and gain values which are 6.29 dB at 4.4 GHz, 4.45 dB at 6.2 GHz. The Vswr is less than 2. The C-shaped microstrip patch antenna finds its applications in commercial WLAN, WiMAX, and in radar application. Keywords: multiband, patch antenna, radar, Vswr, WiMAX, WLAN. Introduction. In the era of wireless communication, the necessity of compact and miniaturized multiband antenna is flourishing rapidly. To satisfy this requirement, a microstrip patch antenna is the available possible solution. Microstrip patch antenna has patch mounted on substrate and ground plane on the opposite side. Microstrip patch antenna are often utilized in mobile and aerospace applications thanks to lightweight and low power consumption during transmission and reception. 1. Although microstrip patch antenna has some limitations like narrow bandwidth and low gain, but its several advantages too, like low profile, lightweight, compact size, financial feasibility, and characteristics of covering multibands with one structure. To beat these nominated problems, various techniques like increasing the peak of dielectric substrate, decreasing dielectric constant 3, and using parasitic patches 4 are want to enhance the BW of the planar antennas. Antennas play an important role in communication system design in terms of operational frequencies, cost, weight, and size. Allocating one antenna for each communication waveband would make the entire design of mobile terminal bulky, not only in terms of size but also in terms of its weight. This is able to also pose questions on the financial feasibility of the system design. The simplest possible solution to the present problem is to style one microstrip antenna with compact size for various communication bands at an equivalent time. 5. 2 Catalogies of multiband antenna. The research study of multiband antennas are often categorized into PIFAs, wire antennas, and defected patch and ground antennas. 6. Authors of 7,8 have suggests few designs for PIFA with multi-communication bands. Introduction of parasitic patches to the traditional microstrip patch antenna is additionally one among the technique for getting multiband characteristics, where within the main radiating patch works at lower waveband while the parasitic patches are introduced to figure at higher frequencies. 9. Authors of 10 have achieved quadruple bands is single planar monopole radiator with low substrate height achieving 4 communication frequencies, which of 11 have proposed a loop structure mixed with monopole to realize multi-bands for communications. 3. Related work looking at simple microstrip patch antenna for single band operation. Numerous microstrip patch antennas are proposed by various authors during this literature review. In 13, microstrip patch antenna has been presented which features a peak gain of 3.5 dB with return loss 30 dB, while in 14 the proposed patch antenna features a gain value of 1.4 dB and reciprocally loss of 25 dB, and in 15 the height achieved gain is 3.4 dB. During this article, a completely unique design of triple band microstrip shirt-shaped patch antenna has been presented, during which the most radiating structure is mounted on FR4 substrate having dielectric permittivity ER equals 4.4. 3 L-shaped slots are etched within the rectangular patch, which increases the inductance of the patch, resultantly increasing the electrical length of the antenna, which produces multi-band characteristic. Therefore, the intent behind this work is to supply a replacement shirt-shaped design for the patch antenna having the capabilities of covering multi-bands of wireless and radar applications. The proposed C-shaped microstrip patch antenna during this work provides multiband characteristics with small size and wide bandwidth, Vswr2. The operating frequencies find its application in C-band. The presented antenna design is additionally compared with another works in term if their sizes, frequency bands, return loss, and gain values, and therefore the results are tabulated in Table 1. For design of C-shaped antenna. Fig 1. Design of C-shaped microstrip patch antenna. As shown in Figure 1, the rectangular patch is of dimensions, LXW, on FR4 epoxy sheet whose loss tangent is 0.02 and height is 1.6 mm. The length and width is taken as 30 mm x 40 mm. The patch antenna is excited using a 50 at feed line for impedance matching. The dimension OD antenna are calculated using a well-known transmission line theory from electromagnetic theory and antenna and wave propagation. The steps for calculating the dimensions are as follow. Step 1, determine the width of the patch. The flow of these construction of patch antenna is like 6 parameters. A. Return loss. Antenna's return loss is the amount of the power reflected from the input of an antenna. Return loss is a quantity often used within RF circuits where the most important thing is impedance matching. Moreover, the winding reception apparatus radiation design ordinarily has a pinnacle radiation course opposite to the plane of the winding. An antenna's return loss may be a figure that indicates the proportion of radio waves arriving at the antenna input that is rejected as a ratio against people who are accepted. It's laid out in decibels, dB, relative to a brief circuit, 100% rejection. Consider the antenna getting used in transmit mode. B. Gain. In electromagnetics, the ability gains of antenna or just gain could even be a key performance number that mixes the antenna's directivity and electrical efficiency. During a transmission of antenna, the gain describes how well the antenna converts input power into radio waves headed during a specified direction. Whereas, during a receiving antenna, the gain describes how well the antenna converts radio waves returning from a specified direction into electrical power. Antenna gain is usually defined as the ratio of the power produced by the antenna from a far-field source on the antenna's beam axis to the power produced by a hypothetical lossless isotropic antenna, which is almost equally sensitive to signals from all directions. C. Frequency, gain, and power relationship. The dependency of power is on both frequency and gain. Gain is defined at a specific frequency. Frequency is independent of power or gain. D. Radiation pattern. The radiation pattern of an antenna is the geometric pattern of the relative strengths of the field emitted by the antenna. The radiation pattern reflects the sensitivity of the antenna in all different directions. E. VSWR. VSWR stands for voltage standing wave ratio and is also referred to standing wave ratio, SWR. It is a function of the reflection coefficient, which describes the power reflected from the antenna. If the reflection coefficient is T, then VSWR is given by VSWR equals 1 plus T, / 1T. The reflection coefficient is also known as the S11 parameter or return loss. The range of VSWR should be from 0 to 2 as a VSWR value under 2 is considered suitable for most antenna applications. The VSWR is frequency dependent. Frequency dependency means the VSWR for the carrier's signal could also be different than for the harmonic signal. Generally, the VSWR is specified as a maximum value for the frequency range of a component. 7. Configuration of C-shaped patch. Antenna in Fig. 1. The configuration of C-shaped microstrip patch antenna is shown. We have placed a sheet of FR4 epoxy there as Fig. 1 shows the patch antenna with the ground plane which is designed in high-frequency structural simulator, HFSS. This antenna was aimed to center frequency at 4.4 and 6.6 GHz, in order to evaluate performance. Moreover, the patch antenna is made from EQ, 1, EQ, 2, and EQ, 3, in the software. During the simulation process, the center is kept unchanging from 4.4 GHz to 6.6 GHz to verify the results that were obtained. V simulation and results. The experimental setup of the whole structure of the spiral antenna is simulated in high-frequency structural simulator, HFSS. With substrate of FR4 epoxy having effective permeability 4.4 and loss tangent 0.02 and mass density, 1900 is taken. As it is frequency independent here, it ranges from 4.4 GHz and 6.6 GHz. The spiral antenna is simulated in HFSS in Fig 1 and Fig 2 shows the result of return loss. The spiral antenna with center frequency at 4.4 GHz at first and then 6.6 GHz and has a gain of 6.29 dB at 4.4 GHz frequency as shown in Fig 3, the gain of 4.4538 dB at 6.6 GHz frequency as shown in Fig. 3. The radiation pattern is also presented in Fig. 4. The VSWR is also shown over here, which is greater than 0 and less than 2, which satisfies the condition in Fig. 5. Conclusion: the constructed and simulated the C-shaped patch antenna having substrate FR4 epoxy in HFSS software. The effective permeability is 4.4. Here, step-by-step procedures for designing the antennas were presented in this paper. The height of the antenna is 1.6 mm and the width of the antenna is taken as 40 mm for impedance matching at 50. Moreover, the patch antenna satisfies the condition of gain and return loss as shown in the above figures, as 2 is multiband frequency, that it can work at frequency of 4.4 GHz and 6.6 GHz. So, this antenna presents polarization with the wide band frequency range.